first sparks on quiet streets, two hearts finding where to meet. But life pulled us apart, left me talking to the dark.
Good evening, everyone. Today I'd like to share our experience with the Truma B10 repair, which initially presented with a broken potentiometer that required careful disassembly. During reassembly, we unfortunately put the coil casing back together incorrectly, turning a straightforward fix into a much more detailed and comprehensive repair process. Oh, and this is how it sounds when the magnetic field is actually too weak. This is the solenoid with the metal housing, which is quite delicate to assemble. Once assembled, it is mounted onto the brass guide, in which there is an iron-containing ferrous valve that can be opened and kept open by two different coil windings. So you can see that's the coil casing, and this is the setup to show if it works or not. So I added 3 more pins to those lines. Left to right, it is holding pin, opening pin. On the right side, it's the ground pin. It usually triggers with 12 volts. And then you can see, if it engages, you hear a click. That's good. And this is the release. So the first coil really works well. Here again. You see it also draws a lot of amperage. And here you can see what I'm doing. And this is the pin for the holding coil. That's the outermost pin. And if you stick it into the 12 volts, it will work, of course. And then you hear only the opening click. The release click is not there. And if you unplug it, you hear the release. So in this setup, I would say it works pretty well. You can also measure the resistance, then unplug everything, and then check that the outermost pin has 300 ohms of resistance and the inner coil has 8 ohms of resistance. So right after we discovered that the coil was the problem and everything worked again, I still found myself in the position that I wanted to learn about the circuit board. So I printed this mount, added a few probes from my oscilloscope, and did a few interesting measurements. I hope you liked them. This is my hardware in the loop setup. So basically the green LED is like in the real controller board. You see that the appliance is in operation, and the red one indicates an arrow. And I've hooked up this to my self-built testing rig. So the left button here is the ionization electrode, and the right button is basically power on and power off. I power this using around about 12 volts. And you can see on the oscilloscope that it's currently running. So I go a little bit back. And let's just see what happens if I turn it off. You see there's some voltage drop. And the green LED has obviously gone. And I turn it back on. And you see that the voltage pattern instantly recovers. So this is the oscilloscope close up. And the upper line, the blue one, that's basically the 2 big capacitors which drain over time. And here it goes back up. Okay, so what's this all about? And the thing is, I didn't know for a very long time how this actually works. And now I understand it. So basically, these are the 2 big capacitors I was talking about. Down here, there's one relay. It's the yellow box. And up here is another one. And basically it works like this. So the red lines, this is the plus 12 volts. And all the red wires here are basically indicating that there's always 12 volts. And then it goes to the control interface here. And then if you connect the switch over here, it basically connects the orange line. And then parts of the circuit board, namely those in orange, will be powered. So if you look at the board, it's quite a complex setup. I've made a hardware in the loop setup where I basically connected only the plus 12 volt, the ground. I connected temperature sensor. Then this is the ionization electrode, this white pin here. And then basically this here is part of the solenoid, which opens the gas valve using the outer one, the green line. This is the holding magnetic coil, and the red one is like opening it. So hold coil and open coil. This red line needs much more amperage than the green one. So how does it work? So if you look at the circuit board, you see that there's this part, which is very interesting. So if we only look at the board, looks like this, and you can see that there's a transistor here. And basically, if you power up the circuit, then this relay here will be powered. And I wondered for hours how this actually works. And turns out there's an electron pump here. It works like this. So let me just get the overlay back. So when the appliance is powered, not turned on, but just powered, like it's always in the van, it will also connect this wire, and this is also a reddish tone, not orange, but a reddish tone, indicating that this line here is always powered. And it means that this capacitor here will be connected to 12 volts, and it will charge not only the positive side, but also the negative side. And if you now connect the switch on the remote panel, then it means that the orange line is powered. And when the orange line comes up, it's also 12 at plus 12 volts. It means also that it goes here, and here's a transistor, and this is connected to the gate. So this means that turning on activates the gate, and this flushes basically all the positive charge here down the drain into the ground. And since there's a diode here, a set diode actually, I show it like this, it means that negative charge will not be able to escape. So basically it stays minus 12 volt here. And the relay itself, it's operated with 12 volts, but it actually only needs 8 volts to engage. So the minus 12 volts and the positive 0, which this line has when the appliance comes up, basically means it will enact, and then it will basically on these two connection pins, which control the relay, it will connect this pin here to that pin over there, and this pin here to that pin over there. So this means if this connection is made from the switch on 12 volts to this yellow line, it means basically that it will put power all the way through the circuit board, all around the major areas, and then it will go in here, and this is the other relay. And in here, it's basically connecting these 4 outer pins, which are marked now. It will connect all those together, and they will all get to plus 12 volts. And as a result, it will charge this capacitor here. But more important, it will go down this line through this diode into these big capacitors. And in return, these big capacitors, they will also power this relay. So the circuit board can charge a lot of energy using the yellow line. It will then load this line here, and then it will go from the 0 to minus 12 volt. It will go over into plus 12 volts to 0 volts. Interesting finding is I can also induce this arrow. For example, now the board is powered up. I power it down, and I wait until this blue line is going below 4 volts, okay? Which is now. So if I now disconnect the plus 12 volts, and then just reconnect it. Oh wait, I need to power up as well. And then if I reconnect it, it will instantly go into an arrow phase. Boop. And here you can see it, the arrow turned up. But we can also go out of the arrow phase. So there's a line, this one. This is connected to plus 12 volts. And if I now go to the capacitor terminal for the plus side, and I issue this very shortly, I try to show all the bits, and I touch it like for only 100 milliseconds or something. And you can see it just turned everything up. The red LED is off. And here you can see that the blue line is all the way up here. And the blue terminal is connected to the positive terminal of the capacitor. So that means that everything is in operation now. Here's the power cycle from the oscilloscope. So the red line indicating the negative voltage, and the yellow line is basically the power on. So after we now have established how the power supply works, I want to focus on something else. So basically, let's see all the components again. So we have a few capacitors, and namely the electrolyte capacitors are of importance right now. So basically this one handles the temperature change over time. This one here handles the coil opening. So there's one shot and it tries to use this to open the coil. Then these two are basically the timers for all the board electronics once the circuit, the power loop is established. And then we have a few tiny ones down here. So basically this one stabilizes the power supply, and this one stabilizes the power supply on the switched on line, so the other part of the board. And this one is our starter. And this down here does some pumping action with transformer down here into the high voltage circuit over there. And one part which is quite interesting is this IC here. So if we go into details, we see that there's plenty connections all over the place. This is an operational amplifier. In particular, it's an LM324N. And it's used to control the board, basically. You can see it's divided into 4 distinct groups. This here is basically the power supply. Once the power switch from the user is enabled, this circuit will automatically power up. And it's basically working like this. It has 2 inputs on each side. So the lower one here is const input, because this is a voltage which is dedicated by only one resistor. And then this other input over here, this is basically the feed from the temperature sensor and the decision you made with the potentiometer in regards to how much the heater should actually heat up. And this is the output. So basically these 3, they form one operational group of this LM324N circuit. And the output here goes all the way here over this resistor to this transistor over there. And this transistor basically enables or disables this relay over here. So this relay basically operates the opening of the valve, the solenoid for the gas, and also it maintains the open state. So there's 2 coils inside the valve. One is for opening it, and the other is to keep it open. To keep it open needs much less power. So this here controls that. So something else which is controlled by this is actually the power supply for this. Once this relay has power, once this is powered up, it will cut the power supply and try to ignite the flame. And that's when these big capacitors come in handy, because they basically are a 4-second countdown. If the gas flame is not ignited within the 4 seconds, this runs out of power, and then it will close the valves again, and the circuit board will go into the error condition with the red LED lighting up, and you need to manually power cycle it. So say, what are the other 3 groups here? So the other most important line are basically these 3 inputs over here. And you can see the white line. The white line is the ionization electrode, and it feeds right into this input pin here. And then there's also constant input over here. And based on these things, it's decided whether the flame is there, then it's 11 volts, or the flame is not there, then it's something way below like 1 volt, I don't know. And it feeds this information into this circuit setup over here. Then there's these other two groups. For this here, I really don't quite understand what it does. It seems to create a rectangular signal of sorts, which goes into the capacitor over here. So maybe it's used with the ionization electrodes of some sorts. Okay, and then the last part is this part over here. So basically, in this section, I think it regulates the negative part of this NPN transistor. You see that it goes on the base pin here, and this goes over there. So basically the output, this is the output of this circuit, basically handles the relay state from the negative line. If the negative line is not connected, it doesn't work. So it both needs basically this transistor to be engaged and also this transistor being engaged. And when both of those are there, this relay will start operation. And then some final words on the temperature sensing. So down here you have the input from the control interface. It's a 12 volt drop, 12 volt meaning 70 degrees, and I don't know, like 6 volts meaning, I don't know, 40 degrees or something like that. And it goes all the way into, wait a second, the wrong pin. The third pin actually goes in here, goes in there, mixes with the capacitor here. So basically this normalizes the input. And also there's a voltage drop going over this line. So basically this here is the temperature sensor on the metal case, on the pressure vessel, or basically on the water container. And you see this is connected to the ground here. So basically, I guess there's more voltage drop over here, the colder it gets or something. And basically these two inputs, the selected power and actual temperature, feed into this pin over here. So basically this regulates the temperature. This regulates if the heating should be engaged based on the information of the ionization electrode. It either enables or disables it. And this here is the part with the ionization electrode. And I think that pretty much concludes it. I want to show you one more time this graph over here. So here you can see that right after the start of the circuit, you see the negative voltage here. This is used to bootstrap the main power supply loop in the circuit. Then you see the yellow line. This is the reference voltage from the power supply. You see the green one, and the green one is actually used to start the heating. It's basically the output 1 of the LM324N. And you see after roughly 1 second, it goes down here, and that makes that tries then to ignite the flame. And you see it took about 2 seconds to ignite the flame. Here you see it has been successfully ignited, and then the power levels come back up because the power loop is then closed again. So you see that it drains power here. That's because during the ignition phase, there's a hold off timer with 4 seconds. And if that current runs out, if that voltage runs out, then basically it goes into error state. And you see after 2 seconds, it recovered and the ignition was successful. And of course, this was simulated by me pressing this power button over there. And then it got back into a steady state and it works again. So basically, here you have it. That's how this circuit board basically works. A close-up and zoom-into version of the schematic I designed with PCB Tracer, which is a very handy tool, you will find in the description below. It's on GitHub, and you can open it in the web browser and just look at the board in detail. You can switch sides, and you can also look at the input and output connectors. There's detailed descriptions on all the important things. There's no port lists and there's no resistance values, but still I think this will be very helpful. Out of curiosity, I did measurements from the temperature sensor, and I also checked out which is the most likely candidate they picked to build into the board. In general, however, I would always go with the genuine port. In this image, you can see all the connectors. The solenoid has 3 lines going to it. However, the ground, even though it's connected to the pinout, it is only a relay to the thermal fuse. So if the thermal fuse blows, it means the electrode won't be able to engage the solenoid, and thus the gas valve will be closed immediately. Then there's also the thermal sensor, which is basically attached to 2 pins. And on the connector side, there's plus 12 volt lines, the on-off switch line, which basically routes the energy flow back to the board. And then there's also the red LED line and the ground. On the user interface, you can also see the rating on the potentiometer, which reads 2.2 kilo ohms. And on the high voltage side, you can see that there's the igniter. This is, however, connected on the bottom side of the board with 2 pins, which is not visible here. And I'm also sorry for the inversion on the x-axis. This is due to my program I'm using at the moment. So finally, thank you all for watching and for your interest in the Truma B10 repair. I hope the detailed steps in fixing the broken potentiometer and correcting the coil casing reassembly were helpful. If you have any questions or your own repair stories, feel free to share them in the comments. Stay safe and happy repairing.
If only for a moment.